Well, I want to thank Dirk for a wonderful introduction, and it makes my talk immensely easier because I can concentrate on how we did it, and he showed you a lot of what we did. I'd like to say one or two things about origins. Bill is correct that we missed out on the golden age we heard so much about yesterday. We've been writing at least one proposal a year since about 1962. And the first proposals were for a 140 MeV machine, and we were in internal competition for tandem Van de Graaff. And this went on for several years, where Van de Graaffs were put in other universities, and 140 MeV machines were put in national laboratories. And there was, about 1964, a caucus in which it was decided to go after a 500 MeV LINAC. If you can't get 140, so try for 500. And through the help of Arthur Kerman, Herman Feshbach, and our theoretical friends, it was decided to go after only an electron machine. And we heard from Fred yesterday that in 1966, we got a phone call saying, will you settle for half? And we have been settling for something like that for ever since. Now, Bill mentioned Peter Demos, Phil Sargent, Stan Kowalski, myself, as people who were frustrated at the kind of machinery that was available and who were pressing the issue. And when the money was appropriated, it became urgent to get a couple of professionals, one in accelerator design, that was Jake Hameson, and he came for a few years. The other was an expert in wheeling and dealing and haggling, and that was Paul Reardon. He also came for a few years, got us rolling, and what we built and what we've operated for a long time is indicated here. I'd like to tell you a few things about it. I'll use my time. I won't go through the whole story, not conceivably. Now, what you notice is that there's been a huge traffic through that place in those years. 75 graduate students have got their PhD theses. That is probably our most important product. Those are the Bates babies. You'll hear from one in the next lecture, and Dirk mentioned that. Now, that work has been carried out by a very small number of people. This is the present distribution. I don't expect you to remember any of this, but I'd like to point out a number of things. If you look at the distribution, you'll notice that the academic staff, research staff, and graduate students overwhelm in numbers, or at least are equal to the so-called support staff. And you wonder, how can you do that kind of thing? Well, what you have to do is you have to have a support staff which is as talented as the graduate students and the research staff. And if you have then 100 very talented people who work very hard, you can do a lot of stuff. And that's the way the place works, with smart people working very hard. There is a consequence, however. The organization chart that Fred showed you may be the way it looks from the dean's office, but on the floor, this is what it looks like. It's a conference among peers. I defy you to find the director in there. I've worked with 2 directors, and for each of them, that's been the organization chart. We have a new management since November. I'd be interested to see a few years from now whether that still applies. You might notice that also looks like a theory seminar at MIT. One other thing that's been remarked upon is that over the years, the generations look younger and younger, especially you notice it when the freshman class comes in. And that's the truth. But at MIT, at Bates, the situation is even more absurd. This is another Flans instructing his elders. Now, okay. There is an opportunity to visit Bates tomorrow. It's open house, and the laboratory is about 25 miles north of the city. MIT is about 25 miles this way. Cranes Beach and Plum Island is about 10 miles that way. And it is a very gorgeous campus. It is on campus, according to MIT's administration. The laboratory is named after William Bates, who was the congressional representative from that district who helped us get that land at a very crucial time. The laboratory, schematically, is shown here, color-coded, with the code indicated at the bottom showing how it's grown over the years. The original proposal contemplated all of that except for the ring out here, which is the project presently underway. It was for 500 MeV to supply a high-resolution spectrometer and a coincidence capability. Now, when we had to settle for half, there was convened in 1967 a summer study in which all the options were vigorously debated. Bertozzi was a forceful presence throughout that. Out of it emerged, and it was a joint seminar with the people at Saclay who were building a machine at the same time. They, however, were not financially embarrassed. They built both sides. We decided to build a high-resolution facility for electron scattering. Now, very roughly, the beam energy now goes up to a GeV. That was accomplished by taking the beam and recirculating it one more time. This was a project that was undertaken by Phil Sargent and Jay Flans and Stan Kowalski, and has been successful. High currents, 1% duty factor, and the work I'll show you has been done mainly with that. We are presently engaged in an upgrade. It's been referred to as the Southall ring experiment. At the end of that, we expect to have approximately 100% duty factor, with the other parameters more or less the same. Now, for those of you who won't make the trip, let me show you some pictures. Here's a view of the accelerator looking at it from the injector. It's not quite as infinite as SLAC, but it's all a matter of perspective. Here's a picture of the same thing now with, at a later time, with the recirculator magnets are installed. They're not really that big. That's a matter of perspective. But those are surplus from University of Michigan. Those of you who make the trip will notice that at least half of the hardware around there is hand-me-downs from one place or another. That's one way of coping with poverty. We have produced and had an operating a complement of spectrometers. I just list them here. This is the high-resolution one. Big project of the 60s and early 70s. Bertozzi, Kowalski, Williamson, Sargent, myself. The medium energy pion spectrometer, Ingvar Blomqvist, Aaron Bernstein, the RPI group. OHIPS, June Matthews and her associates, Big Bite, Claude Williamson, Ed Booth with a Pi Zero spectrometer. And now these have all been operating. Now we're in the process of building something called an out-of-plane proton spectrometer system. Let me show you some pictures. There's the high-resolution spectrometer system, ELSI here. These are four magnets of a chicane which allows us to do electron scattering at precisely 180 degrees, which is important if you want to get the magnetization densities that Dirk was talking about. This is a project that was funded by the government, DOE or ERDA or one of those outfits, and done by the University of Massachusetts, Jerry Peterson and Jay Flans, who was a graduate student there. That was his thesis. That's an example, one good example of another thing that makes the laboratory viable in spite of the small numbers, and that's the contributions of the users. This is a good example, and that system worked beautifully. Just one further remark. That, some of you may recognize, is Bill Lobar, who claims to do everything, and that's proof. These are coincident spectrometers in the Southall. This is the one, this is MEPS, this is OHIPS. This one was designed by Ingvar Blomqvist, and this one was built out of surplus magnets. And here, schematically, what the out-of-plane spectrometer system will look like. This is the OHIPS, and here are four quadrupole-dipole combinations whose intent will be to measure the out-of-plane coincidence protons from proton knockout. And in fact, one of these has already been built and tested and used in an experiment, the first ever measurement of the so-called fifth response function. This was using polarized electrons on a carbon and deuterium target and measuring the angular distribution out of the plane of the knockout protons. This is an experiment that was jointly done by University of Illinois group. We're working under Papa Nicholas and Bill Bertozzi's group at MIT. Now, why did we initially settle for just a high-resolution spectrometer? Well, you must remember the time. The time was the early 60s, middle 60s, when the shell model was, and the mean field was in the process of being developed. There was a lot of interest in how can the nucleus coexist as a collective, manifest collective properties, and how does that come out of the motion of nucleons in a mean field? How is that, all that story put together? And the available data were mainly moments, the integrals over the radial wave functions. And the form factors give you the distributions. Now, there were some data, and they were enticing, but they were very fragmentary. And the reason was twofold. One, the available currents were very small. 1 microamp was a terrific current, and the resolutions were awful. The best was 10 to the minus 3, and that was insufficient to resolve very interesting states. So what was done was to build a system that would use every electron that the accelerator would provide. In the case of the Bates accelerator, it was like 10 to the minus 3. and designed the system so that you could do resolution, you could achieve resolution in the electron scattering of 10 to the minus 4 or better. So a very wonderful project, worked beautifully, as I will show you. Here is a very good example of the kind of thing that can be done, has been done, and the reason why the resolution is so important. Here is gadolinium-154, where previous spectroscopy had indicated that the low-lying states could be described as a mix of a rotational band, k equals 0. Where is this? Beta vibrational band and a gamma vibrational band. And the high resolution was important for two reasons. One, of course, is to separate the states. The second, if you look at the 0 plus beta and the 2 plus beta, if the resolution weren't very good, you wouldn't see that coming out of the background. So those two major motivations. How much time do I have?
10 minutes. Doesn't work anymore.
Yeah.
Sorry.
Okay. So here are transition densities. Based on of the three 2 plus states, the rotational state at the top, the beta vibration in the middle, and the gamma vibration at the bottom. And as you can see, the location of those distributions beautifully support the collective description. At the same time, of course, there was and had been underway a very extensive set of calculations by John Nagley and many of his collaborators on the microscopic description of these transitions. And here is the ground state density for the same nucleus. One is theoretical and the other is experimental. And the differences are not visible in a display like this, but they are in the region that I've indicated in color. Now, there is, of course, by this time, several thousand spectra, form factors in all regions of the periodic table. Here, for example, is a series of isodensity distributions in the same region of the periodic table as I just showed you. And up until yesterday, I had the impression that the theoretical activity had more or less subsided in this area, but I was happy to hear from Steve Koonin that there is now a new initiative to refine further the mean field, and it would be very interesting to see whether the more vigorous computers can cope with data of this kind. Dirk showed you some data on the lead region, which I will therefore skip, and move to what has been a preoccupation in the laboratory for the last decade maybe. And it has to do with the connection between the nucleon-nucleon force and the current in the nucleus. Oh, there we go. The nucleon-nucleon force generally is understood in its longest range to be the exchange of a pion, and that pion should manifest itself if it's charged in a current. and that current should be detectable in an electron scattering experiment. This is the first statement that should be manifested as a current, which should be detectable, was pointed out by Felix Villars in the late 40s. And it has taken until just recently for that to become sorted out in a very systematic and almost believable way. The present agenda in nuclear physics is summarized here. And in order to get at those questions, there is imposed on us a number of experimental requirements that we have been systematically working to achieve. You have to, if you want the short range, you need high Q. High Q implies low cross-section, which therefore experimentally implies high luminosity, product of luminosity, solid angle, and detection. This should be epsilon, detection efficiency. You want to do the coincidence experiments. That implies a duty factor. Many of the interesting amplitudes are small and have to be extracted in an interference experiment. That implies spin in the beam, target, and the recoil. And because one is getting at the fundamentals, you want to use simple targets. By simple meaning few hadrons, like the deuteron and the helium-3 and the triton. Experimentally, of course, that theoretical simplicity comes very expensive. Now, to get the polarized beam, there was, as Dirk mentioned, as frequently happens, an experiment gets started, you produce some piece of hardware specifically for that experiment, and it turns out to be generally applicable for a long-range program. So an investment that may appear to be large for one small experiment, extended over the life of a program, is per year, or however you want to measure it, not bad at all. And the polarized electrons appeared in the laboratory from Vernon Hughes and Paul Sauter and Mike Lubell and the students from Yale who scattered around to, and with the work of Stan Kowalski and George Dodson, we undertook to measure the interference between the photon exchange and the Z exchange and the elastic scattering of carbon-12. We measured the asymmetry, left polarization minus right polarization of the electrons. The nuclear form factor drops out, and one gets this interference term directly. The polarized source, once again funded by DOE. Construction started and carried almost to completion at Yale, then brought to Bates and installed. Here is a picture of it. The experiment, very simple. There is the entire laboratory. There's the injector, there's the accelerator, beam lines, detector systems, all requiring careful control on the systematics, because the effect is very small, the order of fractional parts per million. Here's the statistics and the data. That's the right minus left asymmetry. That's a Gaussian over that number of orders of magnitude. One is confident in the statistics. Systematic errors. These are the final errors. These are in parts per million. And there was a correction, which at one stage was a source of considerable despair, but which finally understood and was that big. yielding a final result. Final experimental result, 0.6 plus or minus 0.14, statistics plus or minus 0.02 parts per million, which yields this factor gamma twiddle. Experimentally, it's this. In terms of the standard model, it's directly proportional to sine squared theta's W, and this is the number given the best available value of sine squared theta, and they're certainly consistent, but not a good measure now of that electroweak factor. How much time? Zero. Zero.
Take a few minutes.
Okay, well, let me not be tempted to take a few minutes just to talk about another program. I think the point I wanted to make has been clearly made, not particularly in the specifics that I would like to have gone to, but it has been, I think, and continues to be, a very exciting program. We are in the process of building this Southall ring, which we expect to finish sometime this year. Already injection experiments have started in putting electrons along this line. This porcupine here is the blast detector, which is another one of these things where there are large numbers of people willing to commit a substantial fraction of their young lives to make, build, and work, and to run. What is the state of the blast detector? Well, last PAC, there were a number of experimental programs approved, time assigned, even though the detector is not built. I forget whether that's 3,000 or 5,000 hours of beam time that's been approved. Technical panels have reviewed it, and they think it's a good thing, can be built, and there's the right crew to build it. DOE has had a scientific review, and the DOE reviewers think it's a nice project. We have yet, however, to hear about money, which brings us back to where we began about the golden age. The original proposals we wrote were sort of 5 pages long. These are voluminous, and I guess I'll quit there, except for one soundbite, which I owe to Phil Sargent. When the laboratory was approved, it was called a $5 million mistake. And we tried to make it run a few years later, and it wouldn't work. It was called a joke. And I think I've given you considerable evidence that it's really a miracle. Thanks for your attention.